Hello and welcome back to part 5 of the Delaware Tech Physics 111 Exam 1 Preparation and Practice Exam covering motion, also known as kinematics. In this section, we're going to talk about velocity versus time plots and the types of information that you can get by analyzing these plots. So here's an example of a velocity versus time plot shown here on the right. The blue line represents the actual plot. We're plotting velocity on the y-axis and time on the x-axis. Time is always plotted on the x-axis, no matter what type of plot you're doing. And you'll notice that this plot is changing velocity from positive values over time. Eventually it reaches zero value between 8 and 10 seconds, and then it becomes negative values after 10 seconds. All right, so the first question says list the various time periods in which different accelerations are displayed, and that there are 8 separate answers. And what you have to remember is you already did position versus time plots, and the slope of those plots was equal to the velocity. Well, now you're doing velocity versus time plots, and the slope of these is equal to the acceleration. In other words, the change in velocity with a change in time or over time. And so now we're going to be calculating accelerations, but before we do that, let's look to see when accelerations are different in this plot. Well, that question is really just asking you which time periods have different slopes. And you can see from 0 to 2, there's a negative slope. From 2 to 4 seconds, the slope is now flat. It's a slope of 0. From 4 to 6, it's a negative slope again. From 6 to 8, it's a steeper negative slope. From 8 to 10 seconds, we're back to a slope of 0. From 10 to 16 seconds, we have another negative slope. From 16 to 18 seconds, again, the slope is 0. And finally, from 18 to 20 seconds, our slope is now positive for the first time in this graph. So you'll notice those time periods I just said correspond to the time periods that you see listed in the next part of this question. So you can just write down the same time periods that are listed here in part B. So part B says, okay, calculate the accelerations for each time period. Well, that's the same question as saying what is the slope of each time period in a velocity versus time graph. The slope of a velocity versus time graph, a v versus t graph, is the acceleration. Remember, acceleration is defined as the change in velocity over the change in time. Well, that happens to also be the formula for the slope of this particular plot. It's the change in the vertical axis, which is change in velocity, over the change in the horizontal axis, which is the change in time. And like any change, any delta, we spell it out as the final version of that variable minus the initial version, and that's true for velocities, and that's going to be true for times as well. Now, determining what's the final time and the initial time is very easy. When you see a range of times, 0 to 2 seconds, for instance, the first time is the initial, and the second time is the final. The later time is the later time. It is the final time. So now it's just a matter of finding the corresponding velocities for each of those two times in order to do your calculation of the acceleration. So let's do one of these calculations. So for 0 to 2 seconds, we know the acceleration, as always, is the final velocity minus the initial velocity over the final time minus the initial time. And if you have a hard time working out which is which, make yourself a little table. I'll show you an example of a table. Here you have the velocities values, and you have the time values, and then make a table where the left side are your final values and the right side are your initial values. You fill these in, and it'll be this value minus this value divided by this value minus this value. Well, I'm just going to take the values right from the graph. We know that any range of times, the range is written as the initial value to the final value, so we just switch them. It's the final time minus the initial time. Well, that's pretty straightforward. And now we figure out what is the velocity at 2 seconds, that will go here, and what is the velocity at 0 seconds, that will go here, and we subtract those two. Well, at 2 seconds, we see the velocity has a value of 10 meters per second. Technically, it's a positive value, so it's positive 10 meters per second. We'll put that in parentheses, and we're going to subtract the value at 0 seconds, which is positive 16 meters per second. And when you plug these in, you get a difference in the numerator of negative 6 meters per second, and you're dividing that by 2 seconds. That's the difference. And that gives you a numerical value of -3, negative 3. And the units, it's meters per second divided by seconds, or meters per second, or meters per second squared. And that is the unit for acceleration. So that is our acceleration at 0 to 2 seconds on this graph. Does that make sense? It's a negative number. Yes, it's going down. The velocity is going down, so you would expect a negative velocity. Now, 2 to 4 seconds, we could plug in the values, and you can see that it's 10 meters per second minus 10 meters per second over 4 seconds minus 2 seconds, but that's just 0. So 10 meters per second minus plus 10 meters per second divided by 4 seconds minus 2 seconds. Well, that's going to be a value of 0. And that makes sense because this is a flat slope here. It's a slope of 0. There is no acceleration. The velocity is not changing. It doesn't mean there's no velocity. It's plus 10 meters per second, positive 10 meters per second. It's just not changing that velocity, and therefore the acceleration is 0. If we look at the 4 to 6 second range, we can plug in 6 seconds minus 4 seconds in the denominator, and the numerator would be the value at 6 seconds. Well, it's 6 seconds. We can see it has a velocity of positive 8 meters per second. And we are subtracting that from the value at 4 seconds, which is the 10 meters per second we noticed already from the previous problem. We plug these in, we get negative 2 meters per second in our numerator, divided by 2 seconds in our denominator, to give us negative 2 divided by 2 is negative 1. Some of you can do this in your head, but if you can't, use a calculator. That's what they're there for. Negative 1 meters per second squared. Does that make sense? Well, yes, it's negative because it's going down, the velocity is going down, and it's not as steep as that very first acceleration we saw in 0 to 2 seconds. In fact, it's only a third as steep, and that makes sense. It's a value of negative 1 meters per second squared instead of the negative 3. If we look at 6 to 8 seconds, we see a large change, so we expect a large negative number here. In this case is our answer. We plug in our 8 seconds minus our 6 seconds in our denominator. At 8 seconds, we see the velocity is 0 meters per second, and we're subtracting it from the velocity at 6 seconds, which we already know is 8 meters per second, positive 8 meters per second. And this gives us a numerator of negative, don't forget the negative sign, negative 8 meters per second divided by 2 seconds, which gives us negative 4 meters per second squared. And that makes total sense because this is a very steep slope and it's pointing downward, so we expect a fairly large number that is negative, and the units are always meters per second squared for acceleration. At this point, I'm going to slide down and the writing will disappear and we'll have to refer back to it. Now, looking from 8 to 10 seconds, we can see right off the bat that we're changing from 0 meters per second to 0 meters per second. There is no change, so there's no change in velocity during that period of time. And in fact, it's going from 0 to 0. So not only is there no change in velocity, we know right away without even calculating that our acceleration is 0. We also know that the velocity at this point is a constant value because the acceleration is 0. But in this particular time, 8 to 10 seconds, that constant velocity is also 0. Just because the acceleration is 0 doesn't mean the velocity is 0, but in this particular case, it is. If we look at the 10 to 16 second range, this is a longer range, we see this long downward slope, and we're changing in time from 10 to 16 seconds. That means the 16 seconds is the final time, the 10 seconds is the initial time, and at 16 seconds, we have a velocity of negative 15 meters per second. So be very careful when you're looking at graphs in the negative range, because the numbers are going in the opposite direction. They are increasing as you go down, not increasing as you go up with the positive numbers. So people often make a mistake. They'll look at these graphs, and if they're trying to figure out a value between numbers on a graph and they're in the negative range, they'll tend to think, oh, I'm at one position when they're really at another. So convince yourself that at 16 seconds, the velocity is minus 15 meters per second. All right. And at 10 seconds, we were still at the 0 meters per second range. And now we're subtracting negative 15 minus 0. Well, that just stays as negative 15 meters per second. And our denominator is 6 seconds. And if you can't do this in your head, use a calculator. Negative 15 divided by 6 is negative 2.5. And as always, our units are meters per second, which we write as meters per second squared. Scrolling our paper up, we now look at 16 to 18 seconds. And if we go back to the graph, and all the writing is going to be gone here, but if you look at 16 to 18 seconds, you can see the slope is flat again. It is a slope of 0. It is an acceleration of 0. It is changing, if you want to call it changing, from minus 15 meters per second to minus 15 meters per second. So there's no change at all in the velocity, and the acceleration is 0. So if you were to actually write this out, you would write it out as the acceleration is our change in velocity over our change in time, and our final velocity minus our initial velocity over our final time minus our initial time. Apologies for the quality of the writing with these styluses. And we plug these in. We know it's 18 seconds minus 16 seconds, and they are both velocities of negative 15 meters per second. And while you can always take a calculator and do this, you know that if this number and this number are the same number and you subtract them, you're going to get 0. And 0 divided by anything, in this case 0 divided by 2 seconds, is still 0 meters per second squared. So the slope is flat, the acceleration is 0. But the velocity is not 0. The velocity is a negative value. It's actually negative 15 meters per second. Now our last range is 18 to 20 seconds. So let's scroll back up to the graph and take a look at what 18 to 20 seconds looks like. And you can see that that's this range here, where the slope is now positive. It's going up, and it is ending up at this value and starting off at this value. So that is a final velocity of -5. Right here is -5 meters per second. You'll see it's midway between -4 and -6 meters per second. And the initial velocity is here, -15, midway between -14 and -16 per second. So you always have to be careful when you're looking at the negative side of any graph to make sure you're actually selecting the correct value. All right, so I'm going to scroll down and we're going to lose these numbers, but remember, we're going from -15 to -5 meters per second when we do this. So we know that we're going from -15 meters per second to -5 meters per second. This is at 20 seconds. This is at 18 seconds. And this is exactly the opposite order you want in your formula. You want 20 seconds minus 18 seconds in the denominator, and you want -5 meters per second minus a -15 meters per second, or if you prefer, -5 meters per second minus -15 meters per second. And when you subtract these two, you notice you can always turn that and that into plus signs to simplify your math if you're doing it in your head, but please use a calculator to make sure you don't make any errors. And you'll see that -5 minus -15 is the same as -5 plus 15, which is a positive 10 meters per second divided by 2 seconds, and that's equal to +5, that's what we get when we divide the numbers, meters per second squared. And this is our acceleration for this last range of times. Now, when we scroll to the next page, we get question number 3, which says calculate the displacement for each of these time periods. So we've already looked at the plot and calculated slopes, which are equal to acceleration, but the displacement can be also determined from a velocity plot by finding the area between the plot line, in this case the plot line is in blue, and the x-axis, which is a bold black line here. So you're looking at the areas between those. So I'm going to quickly show you in shading what that looks like. It's these areas. It's that area, it's this area, it's this area, it's this area, and then there's no area here because the plot and the x-axis are the same, so there's no displacement in that range of time from 8 to 10 seconds. And that makes sense because the velocity at 8 seconds is 0 and the velocity at 10 seconds is 0. And if you're not moving for 2 seconds, you're not adding anything to your displacement. And now your velocity after 10 seconds becomes negative, so now you have negative displacement. You're going to the left, and you continue to have negative displacement, and then more and more and more. And now you're still pointing left, but you're increasing your velocity towards the positive, you are still uh, creating a negative displacement because you are still traveling in the leftward direction. So now that you've seen the whole area for this plot that represents displacement, let's look at the individual slices that represent each period of time. So from 0 to 2 seconds, we are interested in this displacement here. And you'll notice that's kind of an unusual shape. It's actually a trapezoid. And while we do have formulas for areas of trapezoids, it's much easier to just break it up into a triangle and a rectangle. And we know the area for a rectangle is base times height. And we know the area for a triangle is 1/2 base times height. Well, these two figures have different heights, but they have exactly the same base. The base is the width in time. It's the 2-second range that's represented by 0 to 2 seconds. So we have an area for a rectangle and an area for a triangle. So our total area is going to be our rectangle area, which is 2 seconds wide. And if we look at it, it is 10 meters per second high. And technically, it's positive 10 meters per second high because it's a positive range of displacement, specifically a positive difference in velocities here. And then we're adding the triangle area that has the same base. It's 2 seconds wide. But now this is an additional +6, positive 6 meters per second. And it's just easier to count the boxes and make sure you're counting if the boxes are 1 wide, and these boxes are 1 wide, but they might be 2 wide or 5 wide or 10 wide. You have to be careful how wide each box is when you count it. So then we add these areas up. Well, this is 20 units. And what is a unit? Well, it's seconds times meters per second. Seconds cancel. So that's 20 meters plus 20 meters, positive 20 meters. And this area is 1/2 times 2 times +6, positive 6. That's equal to another +6 meters. So our total displacement is positive 26 meters for this area. And we could do this for each of these, and I'm not going to spend a lot of time doing it for each of these. I want you to see that in from 8 to 10 seconds, it's a displacement of 0 during that period of time. The 8 to 10 second range, displacement is 0. But you also have other areas where you have to be careful about adding up shapes. For instance, if you were just asked for 14 to 16 seconds, it's not one of the ranges given here, but you can see that's also a triangle plus a rectangle, and both of these are negative values. So let's scroll down and pick another region. We can pick one of the others that are listed here. If I scroll down, we're going to lose our writing. But if we pick one of these later periods of time, say the last period of time, which is the 18 to 22nd period. So if we scroll down to the 18 to 22nd, scroll back up, you see that again we have an unusual shape. You have to kind of complete it yourself with a vertical line, and then note that it is a rectangle plus a triangle. And the rectangle, you'll notice the bottom of the rectangle is between the two bold lines. It's actually at the -5 position, the -5 meters per second position that we saw earlier. And the bottom of the rectangle is at the -15 meters per second position. So you have to keep that in mind when you're figuring out the areas of these. So the width of each of these, in other words, the base of each of these is 18 to 20 seconds. That's a 2-second range. But let's add up our different areas, and I'll do it up here so we don't have to keep scrolling back and forth. We've got our total area, which is going to be equal to our area of a total area of a rectangle plus our area of a triangle. Our area of the rectangle is 2 seconds base and a -5 meters per second height. And then we have a triangle to worry about. It's 1/2 times the same base times its height. Well, this height is going from -5 to -15. It is a negative value because it's below the line. That would be a difference of -10 meters per second. And when we take a look at each piece, we see the first piece is equal to -10 meters. That's that displacement of the rectangle. And the displacement of the triangle, right here, 1/2 times 2, well, that's just 1, times -10, is another -10 meters of displacement. So our total displacement is -20 meters for this full area under the curve here between our blue plot and our x-axis. That's a displacement of -20 meters for the 18 to 20 second range, Okay, so now you see how to do displacement calculations. I'll leave it to you to calculate the ones we didn't cover in this particular section. And the answers are all worked out and explained in the back of this practice exam. So looking at this next page here, it says at what time or times is the object doing various things. So this is the exact same velocity versus time plot that we've been looking at for the past couple pages. And now we're actually analyzing the plot to figure out what is actually happening. What is the object actually doing at each time point? So the first question says, at what time or times is the object stopped? So what does that mean? So you need to know not just what the answer is, but why the answer is the answer it is. So what does it mean to be stopped? Well, what it means to be stopped is that the velocity is 0. It's 0 meters per second. Well, when is it 0 meters per second? Anytime it hits that axis. Well, you can see right there, that is the 8 to 10 second period of time. Any time between 8 and 10 seconds, the object is stopped. Part B says, when is it moving in a positive direction? Well, remember, what is this plot representing? Well, the velocity, anything above the axis is positive velocity, anything below the axis is negative velocity. What does positive velocity mean? It means it's moving to the right. What does a negative velocity mean? It's moving to the left. So anytime you see positive values, that is a velocity that represents moving in the positive direction. So that would be anytime you're above the x-axis. So in this case, that's the entire period of time between 0 and 8 seconds. Once you're at 8 seconds, it's not moving at all. And after 10 seconds, now you're moving in a negative direction. You're moving to the left. So this graph only goes to 20 seconds, so it's 10 to 20 seconds represents moving in the negative direction. If you had something that only went below the axis for a short period of time, that period of time that was below the axis would be in the negative direction, pointing to the left. Okay, so I've shrunk the screen and I've rewritten it so you can see each of the previous answers. And the next question, part D, says, when is the object increasing its speed? Now, speed and velocity have different meanings, so it's important to understand which one you're talking about. Let's talk about velocity first. When is it increasing velocity? So the velocity is this axis, and anything at the top is higher than anything at the bottom for velocity. So anytime it's increasing speed, that is when you have a positive slope. Well, the only time on this graph where the velocity is increasing, where the slope is positive, is this very last time period. So the velocity is increasing from 18 to 20 seconds. And this is where we have issues about definitions. When is the speed increasing? Well, speed doesn't care about direction. So down here is a fast speed, and up here is a fast speed. Here is a low speed, and here is a low speed. It just happens to be these are negative speeds, these are positive speeds, but speed doesn't care about direction. It doesn't care about positive and negative. So speed, to gain speed, it means you're either increasing this way or increasing this way for speed. So while velocity is only increasing between 20 and 80 seconds in this particular plot, speed is increasing in this period of time from 10 seconds to 16 seconds. If you're asked a question like this and you're given the option, circle the one you're more comfortable with and answer that one. If it's speed or velocity, you say what you're referring to. All right. Part E, when is it decreasing speed? Well, let's talk about when it's decreasing velocity first. Well, it's decreasing velocity anytime the velocity is coming down. And that would be 0 seconds to 2 seconds. But it's also from 4 seconds to 6 seconds and 6 seconds to 8 seconds. So that whole range of 4 to 8 seconds, the velocity is decreasing. The velocity is also decreasing from 10 seconds to 16 seconds. So that's what the velocity is doing. But what about speed? Speed, to decrease velocity, means it's coming closer to zero. And coming closer to zero, the only time, well, there are multiple times when that happens. The speed is decreasing here, except for this, where the speed is not changing at all. So the speed is decreasing again from 0 to 2 seconds, just like we saw over here, and from 4 to 8 seconds, just like we saw over here. But in the case of 10 to 16 seconds, velocity is decreasing, but speed is increasing. We already made note of that right here. But from 18 to 20 seconds, velocity is increasing, but speed is closer to zero. So we would include the 18 to 20 second range here. Now, on an exam, are you going to be asked for every time period? No. If you give one time period with the correct explanation of why you picked that, that's good enough. You don't have to give an exhaustive list of all the time periods. All right, and the last part of this is when is it moving with constant velocity? So it doesn't just say constant velocity. There are 3 times with constant velocity on this graph. There's here, here, and here. Well, we'll call that period 1, period 2, and period 3 down here. I know this is a very busy chart at this point, but there are 3 places where the velocity is constant. Velocity is constant means acceleration is 0, where the slope is 0. It is a flat velocity curve at those points. The first one, number 1, is constant positive velocity. It's constantly positive 10 meters per second. Well, that's moving and it's constant velocity. So we can say between 2 and 4 seconds, because that's a velocity is constant at positive 10 meters per second. But we could also say it's constant at section 3. That is from 16 to 18 seconds, where the velocity is constantly negative 15 meters per second. You might say, well, why can't we use the period of time from 8 to 10 seconds? That's a constant velocity. Yes, it is constant velocity, but in this case, it is constantly 0. So we would say it's not moving relative to whatever we're measuring it against. And therefore, we wouldn't include it in part F. We would include it in part A, where it is stopped. And we'll stop here for this particular set of problems. You will notice the next few pages are another whole series of velocity versus time problems with a different velocity versus time graph. You can do those on your own. The answers are in the back. They follow the same rules that we just went over. So we'll stop here.